Thank you all for joining me this morning on this fairly technical talk about the Android build system. My name is Eric. I'm the developer of ProGuard, the open source obfuscator and optimizer that's part of the Android SDK, which you may have used before. I started ProGuard as an open source project about 14 years ago, and that grew and grew out of hand a little bit. So at some point, I started a company around it. So I'm now the CTO at my own company, GuardSquare. I can wear a white shirt and call myself CTO. At GuardSquare, we develop ProGuard still as an open source project, and DexGuard, on the other hand, as a commercial product. And DexGuard is an extension of ProGuard that focuses on processing Android applications, making them better protected against reverse engineering and tampering. Let's see, today, of course, I'll be talking about Jack and Jill. Jack and Jill are developments of Google's Android team, and I'm not affiliated with Google. I'm just an independent observer, but of course I'm fascinated by anything that happens to bytecode, and that's why I've followed what has been happening with Jack and Jill a little bit, and I've done some experiments, and I'll present some results of those today. Of course, still, ProGuard is my favorite piece of software, and I'll mention it in the presentation whenever I can. So what I'll be talking about today, first of all, I'll go fairly deep into the technical details of the build system with Jack and Jill. But then I'll resurface and I'll talk about the practical implications, how that affects us as Android developers at various levels. So it affects me because I'm working on bytecode manipulation, but it'll also affect all of us as Android application developers. And I'll try to clarify and explain what happens there. First of all, the Jack and Jill names are acronyms, fairly meaningless. But essentially what it says here is that these are compilers for Java source code going to Delphic bytecode. That's the essence of what they do. Why would Google rewrite the original build system that they already have? There are certainly technical reasons, and I'll mainly go into those in my presentation today. But there may also be legal reasons, perhaps. All of the Android tools are owned by Google and mostly licensed under an Apache license. So they may want to take some more control over that. And there may be strategical reasons also. So there's this tug of war between Google and Oracle, and maybe part of that as well, but that's in the realm of conspiracy theories, and I'll leave that to your imagination. So I'll mostly focus on the technical part, and first of all, the easy part. How do you enable Jack and Jill? Well, if you're rebuilding Android from scratch, the entire Android environment with the AOSP, the Android open source project, then it's actually already the default. So instead of using the traditional compilers, you'll be using Jack and Jill by default. On the other hand, if you're still building apps, and that's what most of us do, it's optional still. So by default, you'll be using the traditional compilers, the DX compiler, but you can enable Jack and Jill to experiment with it using a simple flag. At least this is the flag that was used in older versions of the Android plugin. In newer versions, you have to use these settings. So you enable Jack and Jill, and you can enable compatibility with Java 8 to use Java 8 features. There's also an undocumented feature that I needed to use at some point to get incremental builds. I'm not entirely sure if that's still necessary today. What happens then in your build process? The tasks will be reorganized, and in the build output from Gradle, you'll see a few tasks with Jack and Jill doing some things to your code. Now, going into some more detail, what's happening inside that build process. You start from the left-hand side, from your source code, the assets, resources, Java source code. perhaps some external libraries precompiled, maybe native code, and all of that goes through the build process to get everything that goes into the application. The assets get copied, the resources get compiled to binary resources, and your Java code gets compiled to Dalvik bytecode. And that actually happens in 2 steps. First, the Java source code is compiled to Java bytecode, and in the next step, the Java bytecode is compiled or transformed into Dalvik bytecode. Now, the build process can become a bit more complex, more extensive if you're using any transformations on Java bytecode. That's an option. It's even supported in the form of the Transform API in the Gradle build system, where you can operate on the compiled Java bytecode to do something in addition to it. Perhaps instrument it to debug it, or instrument it for performance measurements, or perhaps to optimize and obfuscate it with ProGuard. So ProGuard is just one of these transformation steps that you can apply. ProGuard takes your Java bytecode, makes it smaller, more efficient, and a bit better hardened and against reverse engineering. ProGuard reads the Java bytecode, but at the same time it reads the configuration file, the ProGuard configuration file that you may have been struggling with in the past. That's the file with all those keep options that you have to look for. And ProGuard also writes out a mapping file, which contains the original names of classes, fields, and methods, and their corresponding obfuscated names, which is useful for debugging any problems, any stack traces that you have in your final application. Now, if you look at this process, it's becoming quite convoluted. You start from Java source code, and then in 3 distinct steps you go through to Dalvik bytecode, and there may be even more steps. So an obvious fault here is, can't you simplify this? If you want to make the build process faster, and that's a continuous effort that's going on, why don't you replace all of these steps by a single step that's more efficient? And that's exactly what the Android team has done. They have created a Jack compiler, which indeed takes the Java source code and compiles it straight to Dalvik bytecode. Except that there is one little glitch there. The Jack compiler doesn't understand the compiled Java bytecode that you have in any external libraries. So if you have jars or AAR files, they still contain Java bytecode, and Jack doesn't understand that code. So for that, they have come up with a solution where they have a JIL compiler, which takes the Java bytecode and compiles it to a new intermediary representation called the JACE format. And the Jack compiler does understand this new JACE format, and it can compile everything together with your own source code to the Dalvik bytecode. At the same time, Jack contains the functionality of ProGuard. It can shrink and obfuscate, and it can read the same ProGuard configuration files, and it can write out the same ProGuard mapping files. Going a little bit deeper into what happens internally, I wanted to give you a flavor of what this code looks like. I've been talking about Java source code, which you probably know very well. I've been talking about Java bytecode, Dalvik bytecode. So say that you have a simple statement in your Java source code, a for loop. If that gets translated to a class file containing Java bytecode, it might look like this, containing assembly-like instructions for the Java virtual machine. This is a stack-based virtual machine, so it's compact and easy to evaluate. I won't go into the exact meaning here, but it gives you a flavor of what is inside there. Now, the DEX compiler traditionally compiles that straight to DEX, to classes of DEX in your application, the Dalvik bytecode format. And that actually looks quite similar, and it has a similar feel to it, except that it is not stack-based, it's register-based. And if you look at those 2 formats, they are very similar, and they're efficient to store. They don't take up that much space. They're quite efficient to execute. but they're a bit inconvenient to process, to work on. They both have their quirks in manipulating them, in representing the meaning of your application. So that is probably why the Android team introduced this new intermediary format, the JACE format. And I've shown that format here for the same piece of code. And you can see that it's more like a slightly higher level format. It's a binary representation of the abstract syntax tree of your application. And that is a bit more convenient to work on if you want to shrink and optimize and obfuscate. That's a bit more convenient. Except the problem here for us as mere mortals, this format isn't documented as opposed to the other formats, so we can't do anything with it ourselves yet. What are the implications? So I'm now resurfacing and becoming a bit more practical. In this build process and all of these changes, how does that affect us as developers? You may be using Java annotation processors. That's a feature of the Java-C compiler, and the Jack compiler supports those annotation processors as well. So if you're using any of those, maybe with Dagger or Butterknife, then you can still continue to do that. On the other hand, if you're using any bytecode processors, then that becomes a problem because there is no Java bytecode in that entire flow from source code to compiled Delphic bytecode. And if you're using other languages like Scala maybe or Kotlin, that's a bit of a problem also because these JVM languages typically compile to Java bytecode, and working from Java bytecode has become a little bit more inconvenient here. And at the moment, if you're using Instant Run, that's not supported yet, but I'm sure that the Android team is working on that. Visualizing that same slide in a diagram here, for instance, say that you have a project that includes Scala code, then you have to go through the Scala C compiler, of course, and that produces Java bytecode. But if you have Java bytecode, the only way to get to Delphic bytecode with the Jack compiler is to go through the Jill compiler first. So that process is more convoluted than it was originally. If you're developing for Scala, with Scala, then it becomes a bit more inconvenient if you really insist on using the Jack compiler. I've also drawn the bytecode processors that you could apply in your process and the annotation processors that are still supported with Jack. Now, again, internally, if you look at the source code of the Jack and Jill project, then you can see that the Jack compiler is actually based on the Java front end of the Eclipse compiler. So, and on the other hand, the Jill compiler is based on the Java front end or uses the Java front end with the ASM4 library. So language developers, which have a lot of time to spare, might work from this side to actually plug into the Jack compilers directly. Now, another implication or consequence of using Jack, of course, is that you'll be able to use Java 8 features. And the features that most developers anticipated was finally being able to use closures. So for instance, if you have a closure as shown at the top here on this slide, that gets compiled to something like an anonymous internal class, which can be used on all versions of Android. So it's compiled in a backward compatible way, so that the code that you write in Java 8 is actually working on all older devices. On the other hand, if you're using the Java 8 feature of default methods, that means that you have methods containing implementations inside interfaces, you'll really need to run your application on Android 7. You can only run that application on Android 7. On the one hand, in your own code, The syntax is different, of course, and the virtual machine needs to support that. And on the other hand, in the Android runtime, there has to be support for various default methods that you'd like to use, and that is only present in Android 7. But in Android 7, you can also make use of the other features that these default methods support, like the streaming API. That's a common example. So if you look at the changes that were made for Android 7, there are, of course, the changes in the build system that I've been talking about. But there is also the change that the Android runtime is now based on the OpenJDK runtime, which implies that you can use, for instance, this streaming API that I mentioned. And if you want to use those default methods, you'll have to have Android 7 because there is a change required in the ART runtime. That's the virtual machine that you have on Android 7. And you also need the the OpenJDK runtime, of course, to make use of the additional implementations in the runtime. Then I've looked at other implications for optimizations, an element that's very dear to me. If you look at the optimizations that are present in the standard Java-C and DX compilers, there's actually not that much. So you may know that if you compile your code with just a standard Java compiler, everything gets compiled quite literally to Java bytecode. If you have unused code, any unused variables, all of these get compiled into the code without any optimizations. The only optimization that's being performed is the inlining of constants, so final static constants, typically. And that's why there's room for a project like ProGuard, which can add all of these optimizations. This is a somewhat simplified list, but there's a whole set of things that you can do to bytecode, and that still has an effect on the performance of the application. So even if you have advanced virtual machines, even if you have the Android runtime, which does optimizations ahead of time, there is still room and an effect of the optimizations that you do ahead of time on the Dalvik bytecode. Say of up to 20% in my experience, and that's not negligible for a mobile phone. Now, initially, Jack didn't contain any optimizations at all. But if you look at Jack in the latest version of the Android plugin, it already does a few of those optimizations. So it can obfuscate names, making the application a bit smaller. It can propagate constants. It can remove unused code. So it can remove that classes, fields, methods, and instructions from the application. And what's promising is that if you look at the development version of Jack and Jill in the open source repository, you can see that they're gradually adding more of those optimizations in the Jack and Jill compiler. So there is some progress here. It's taking months, but, well, I've worked for years on it, so that's no surprise, perhaps. But they're getting there. Just for out of interest, I've also compared this with Redux, which is a Facebook tool to take APK files and process them and create optimized APK files. Redux also performs a number of those optimizations. And one of the special things that it does is that it optimizes the layout of the code. And then, of course, I'm very enthusiastic about our own software. I've also compared it with DexGuard, and I've had to shrink the table here a little bit because DexGuard performs a whole additional series of optimizations, because DexGuard not only looks at the bytecode, like ProGuard and like the Jack and Jill compilers, but DexGuard also looks at the resources and assets and native libraries and the manifest file in your application, and it optimizes all of that together. And of course, if you look at more things at the same time, there's more you can do. So just as a bit of background here, DexGuard looks at everything, and it is compatible with ProGuard and optimizes and obfuscates everything together. So that's a lot of theory. I've then done some experiments. So this is the final part of my presentation where I'll show what you can expect if you run Jack and Jill or the various other compilers on your app. And for that purpose, I've taken the Google I/O app and I've compiled it in various ways. At the top, you can see a number of experiments with the traditional tool chain, with the DX compiler and the Java C compiler. And if you do a clean build, it takes about a minute on my computer, not terribly fast. But if you do incremental builds, changing a number of files, changing just a single file, then that speed will increase, so the build time will be reduced. Then if you start enabling ProGuard in the build process, and that's a somewhat surprising observation maybe, a clean build with ProGuard is actually faster than a clean build without ProGuard. And that's surprising because there's this additional step in the build process. And the reason is that ProGuard, quite early in the build process, takes your Java bytecode and shrinks it down to something that's significantly smaller. And the rest of the build process then has less work to do. And as a result, the overall performance of the build process, the overall build time is, the build time is smaller. Now, on the other hand, if you also enable optimizations in ProGuard, that takes a whole lot more time because optimizations are complex and you have to pay in build time for that. I've also compared it to DexGuard, which provides similar build times as ProGuard, a bit longer because there are more optimizations. And then in green, I've I've added results for the Jack toolchain. And also somewhat surprising, perhaps, the Jack toolchain, the initial clean build is quite slow. And the reason for that is that there's this Jill compiler, which has to take all of your libraries, all of your external dependencies, and convert those to JSON bytecode, and that takes a lot of time. Now, those compiled libraries are then cached, so the next builds are faster. So this is just the initial price that you have to pay there. So subsequent builds, incremental builds, where you change the number of files, a single file perhaps, they are significantly faster. Maybe somewhat surprising here is that the Jack compiler isn't faster than the traditional tool chain. So that's something that they're constantly working on, I'm sure, but at this point, the build process isn't faster yet. And then the final line here is where I also applied minification in the build process. And that, again, just like with ProGuard, it takes some more time. Then, once you've built your application, I've also looked at the application size. And if you use a traditional tool chain without any optimizations, for the Google I/O app, you get an app that is about 3.1 megabytes large. But once you start enabling minification and optimization, you get something that's a lot smaller, approximately 1.9 megabytes. And that's approximately the same for Jack or the traditional tool chain with ProGuard or the tool chain with DexGuard. DexGuard does a bit better, of course. Now, once you start installing that application on the device, you're also interested in the performance of that application. And for that, I've done a test with the caffeine benchmark. It's my favorite benchmark because it just tests bytecode performance. It doesn't look at I/O performance. It doesn't look at GPU performance. And I've run that test on with the various compilers. For Java C, you get a score of something like 50,000, and the larger numbers, the better in this case. The Jack compiler, by default, without any changes, already provides a small improvement, something like almost 10%. But then if you apply a ProGuard instead with a traditional tool chain, you still get an improvement that's significantly better in this case. And if you apply DexGuard again, it's still faster. So that's an interesting observation here, is that you get that improvement on old virtual machines, on Dalvik virtual machines, on old versions of Android, but you also get that performance improvement on new art environments. So even if they do a lot of optimizations and they're a lot faster than their older counterparts, there's a relative performance improvement with any of those optimization techniques on bytecode. So you can do some things ahead of time to really improve your application. So in conclusion, looking at the build system internally, there are huge changes. A lot of tasks are being moved around. The bytecode representation is different. But on the other hand, there is also a clean implementation inside. So there's a new Jack compiler, and there's even some indication that there's room for plugins there. So in the future, maybe external developers can plug in their own optimizations, perhaps, in the Jack compiler. At a slightly higher level, if you're a developer of languages and tools, there's a lot changing as well. Because of this different build process, these different build steps, and there's no longer any Java bytecode to operate on. And there's this new intermediary representation. And finally, if you're an Android developer, an application developer, then you're, of course, looking forward to more efficient builds. They're not there yet today, but I'm sure they're working on it. And, of course, you can use the new Java 8 features without needing any additional tools like retrolambda, for instance. If you want to learn more about this, you can, of course, consult the various pages of documentation that Google provides. You can look at the source code of the Jack and Jill compiler. You can find these references in my presentation later on. And that actually concludes my part of the talk. So thank you. If I'm not mistaken, we have plenty of time for questions, so feel free to ask. There's a microphone there, or just go ahead and I'll repeat your question.
So earlier you mentioned that Jack improves bytecode performance as well as ProGuard. Can you talk a little bit about what bytecode performance is and why it's important?
Okay, so I've talked about bytecode performance and how Jack and the other optimizers improve that bytecode performance. Bytecode is the code of your application. So you write Java source code, and all of that gets manipulated throughout the build process, and at the end you hope that an efficiently functioning application comes out. Now, for some applications, that's more important than for other applications. If your application is just using simple GUI components and delegating to all of the work to the Android runtime, then the performance of your application per se doesn't matter all that much. But if you're doing any sort of somewhat more complex computations in your application, you want that code to be optimized as much as possible by the compiler. And that's why these compilers are important to you too, even if they are invisible and doing their work in the background without you knowing and even seeing what's coming out of it. So, yeah.
How would you use the Jack and Jill compiler for library projects? So you could use like Java 8 features.
How would one use the Jack and Jill compiler for library projects? I guess at this point you don't. That's an interesting thing. So libraries are still represented as jar files or AAR files. They contain Java bytecode, and for that you would use a traditional Java C compiler. And also for that you would use ProGuard if you want to optimize or obfuscate it. Conceivably, Google could move in the direction where these AR files not only contain class files, Java bytecode, but also JS bytecode, so that that code doesn't need to be translated the first time you use those libraries, and that was what takes up this much time with a clean build. So if that would be part of the AR file, that would be far more efficient. But that, of course, requires developers to pick up that functionality. It's not there yet, but it's a possibility. I don't know if they even intend to do anything like it. Yeah.
I traditionally use ProGuard just on my release builds, but you made a really interesting point that there are some ProGuard rules you can use that will actually make your debug builds faster.
Yeah.
Have you kind of published any guidance around, like, here's a set of things you should run, like maybe it's just shrink? Like, I think everyone would really benefit from that if there was some advice.
So your build can get faster if you use ProGuard to just shrink, minify the bytecode, but you don't want to obfuscate your code while you're debugging. That would be rather painful, I think. And you don't want to optimize the code because then the build time becomes longer, and that's a bit painful also. So you would use the options don't shrink, don't optimize, don't obfuscate, don't optimize, but you would let ProGuard shrink the application. A slight disadvantage here is that you have to make sure that you have to have the proper keep rules in your configuration file. So what people often do is they work on their application, it works at the end, and then they need to run ProGuard because it has to be minimized. They run into the multi-dex issue and so on. And at that point, they start working on the keep rules to make their application work. So if you use ProGuard in debug builds, you also need to make sure that you have the proper keep rules while you're developing the application.
That's actually an advantage from my perspective.
That's an advantage, yeah. Well, everyone's time is precious, and no one wants to do any stuff that they don't really need to do. But this can be an advantage if your application is very large, using external libraries, and you're perhaps only using small parts of those external libraries. ProGuard will remove all of those unused parts, and that can take a lot of, that can save a lot of time at build time.
Another thing you can add to the list of incompatible is Android data binding. It's not compatible with Jack and Jill.
Data binding.
As far as build time comparisons, the one I really want to see is Jack and Jill versus Java C plus retro lambda. So we care about Java 8, but retro lambda I think is it faster than that?
I haven't made that comparison. In my team, they've done some tests, and I think the Jack and Jill compilers have slightly better output for Java 8 code for closures, slightly more optimized, but I don't know about build times. I can imagine that it's faster because it's all done in a single process, but apparently that's not that obvious, of course. Yeah, so I don't really know.
Switch because of the Android data binding design.
Yeah, yeah. I don't have a definite answer there. No. Yeah.
Do you have any knowledge of the, it's experimental right now, do you have any knowledge of timeline in moving into like an official beta or a true GA release for Jack and Jill?
No, I don't have any special knowledge about that. It's more than a beta right now. It's in everyone's Android SDK or in everyone's Gradle build system. It's just a matter of enabling the flags, so you can use it. It's usable.
Sure. I just that experimental tag always.
Yeah, I don't think they're using the experimental tag anymore. But, yeah, it's still a young product.
So NextGuard can detect repackaging?
That's correct.
How are you able to do that?
It has a number of techniques there to detect tampering with the application. The most obvious one is checking the certificate of the application. So who has signed this application? And if anyone has tampered with the application, he needed to re-sign that application as well. That's something you can implement yourself, but that's something that NextGuard can do transparently. That's one of the techniques. There are some other techniques as well. more questions?
Can you explain what you mean a little bit when you say, I think you said Jack was built on ECJ, or?
Yeah, if you look at the source code, you can see that it depends on the ECJ library. So that's the front end that parses the Java source code. But then very quickly on, it moves to internal representations that are specific to the Jack and Jill compilers. So this is just the front end for parsing the Java code.
Okay. And so basically that's, I'm pretty unfamiliar with that, with this whole concept, but like, so Eclipse has their own, kind of similar to what Jack is to parse the Java source code.
Yeah, Eclipse has its own compiler to compile Java source code to Java bytecode.
Okay.
And the Android team has used the library to, to parse that code as well. So it's not a trivial thing to change to a different language. It's not just swapping out a library there. Okay, well, I'll be around all day. Thank you, everyone, for attending. Thanks.